All right, folks, let me begin. Actually, we have a minute. And today is when we actually begin jumping a little bit into the subject. The introductory class was not meant to be particularly full of information. It was mostly a filler. I introduced the lectures to you and what we would be covering. But starting today, most of machine learning and most of signal processing is all about linear algebra. So we're going to start our actual topic with a couple of lectures on linear algebra. Then the rest of it is going to be optimization and probability. We will cover optimization. I will leave probability to folks. Can you mute yourselves, please? Hello, mute yourselves. Unfortunately, I don't have the ability to mute everybody on entry. So if you don't mute yourselves, you will be disturbing the class. So anyway, Alex believes linear algebra is very scary. I hope it is not, right? You're going to be spending the entire semester talking about linear algebra. What we will be doing today is a linear algebra refresher. Pretty much every one of you must have taken a linear algebra course. That was a requirement for this course. So you are familiar with all the ideas I'm going to be talking about today and then in the next class. And yet, maybe, just maybe, some of the things I will tell you. So, this is a refresher. It's reminding you. And yet, maybe, just maybe, some of the things I tell you will be new to you. And so here's an old meme I found somewhere. You learn something new every day. Not really. Whatever you thought was new is old. Somebody knew it well before you. And often that person is you. And so we're going to learn something old today. Let's go ahead. I highly recommend that everybody goes through Gilbert-Stein's. Can you mute yourselves, guys?
It's the classroom.
But I muted the classroom.
It's the classroom in Pittsburgh, DHA.
I thought I had muted it. Yeah, okay. So we need one of the TS to be in the classroom, I was told. Anyway, I highly recommend this book, Fundamentals of Linear Algebra by Gilbert-Stein. It's very important to be comfortable with linear algebra because it's going to appear repeatedly through the course in the form of eigenanalysis, singular value decomposition, and factor analysis. And also, in terms of the properties of matrices and such like. So we're going to, so it's understand it. We're going to go over all of the basics, and I'm going to use, and since our purpose is to use all of these tools and techniques we'll be looking at over the course on signals, I'm going to apply them to signals. Specifically, I'll be using sound and images as examples. Today's lecture is going to be all about definitions. It's a very small subset of all that's used, but it's an important subset intended to help you recollect things that you always do. So why use linear algebra? Now, linear algebra is an amazing tool. Firstly, it greatly simplifies notation. Here's this little equation to the right. I have a double indexed variable a single indexed variable x, and another single indexed variable y. And I have this ugly equation to the right where I'm summing the product of x and a over one index, multiplying that by y and summing it over another index. But when I write it in algebraic form, it's just going to look like x transpose ay. It's just a very simple multiplication. So notation is simpler. Intuition, you get really convenient geometric interpretations. And of course, code, you can write this ugly loop to the left or this little equation to the right, and most of us would prefer using the one to the right. So it has practical reason applications. But then there's the intuitive and applications, the ability to abstract that it brings forth. enables us to do all sorts of things. Like, see this image to the left, this little cube rotating and doing all sorts of things. All of those operations, almost all of those operations are done using simple linear algebra. Or here's this other example. I hope you can hear the sound. Can you hear that sound? Okay. So that's just a little bar from Bach's Fugue in G minor. This is a spectrogram of this little bar, and using a very simple linear algebraic operation, something that never does anything more than just algebra, I can derive these 4 things from it. Come on. Why will it? So what happened there? I did not use any prior knowledge of music. I did not use any prior knowledge of what was the composition of the sound. Just through a little algebraic manipulation, I managed to figure out that there were 4 notes in it. I managed to figure out what the notes were and even how they were played. So this was the first note. Struck once. This is the second note, struck twice, and here's the bar. I hate this thing. So that entire thing was done with linear algebra. So we're going to go through a lot of definitions. We're going to review what vectors and matrices are, some basic operations, matrix types, their properties. And in the next class, you're going to talk about simultaneous equations, projections, eigendecomposition, and singular value decomposition. Now, most of the fun stuff is in the next class, but you're not going to understand much of it if you don't actually sit through today's class. So let's begin with vectors and matrices and what their operations are. What is a vector? Can anybody explain to me what a vector is? Anybody? What's a vector? Arrangement of numbers. That's it. A vector is simply a rectangular or a horizontal arrangement of numbers the way we are talking about it. So here's an n cross 1 column vector. Here's a 1 cross n row vector. A column vector has the numbers arranged as a column. The row vectors are arranged as rows. And for some reason, every time there's a message on chat, this thing makes a boinking noise, and I have no idea how I can shut it. So you'll have to bear with it, guys. Keep posting messages and enjoy the music. Anyway, a bunch of numbers of this kind just by itself is actually useless. It's a meaningless mathematical object. For us, it has to make sense. So each of those numbers has to refer to a specific quantity. Now, geometrically, a vector represents the net displacement in space. So if the displacement is from origin, then the vector represents a location in space. This vector over here, which is a column vector, represents a location in space. So this one specifically is the vector 5, 2, 13. But then how does this set of numbers represent a location in space or a displacement? Each component over here actually represents the number of steps along a basis direction. So without knowing the basis direction, this set of numbers cannot be interpreted. So when I have something like ABC, this really represents a location given by A times X plus B times Y plus C times Z, where X, Y, and Z are some length in some direction, some other length in some direction, some other length in some direction. So we can use circular logic and call them vectors as well. But there are these 3 basic directions with their lengths. And so this vector actually represents the number of steps along those directions. So here I have the red, blue, and green, the little arrows. represent my bases x, y, and z. So 5, 2, 3 means that I'm taking 5 steps along x, 5 copies of x, 2 steps along y, and 13 steps along z to arrive at this location. Now, typically when you look at a vector, nobody tells you what these basis directions are. And when these are not given, they are implicit. We use the standard bases, the so-called orthonormal bases, where you have 3 vectors. The 3 bases are all at 90 degrees to one another if you have a 3-component vector. If you have an n-component vector, you have n bases all at 90 degrees to one another. And the characteristic over here is that moving along one direction results in no movement at all along the other directions. And all of these bases are unit length. Again, without specifying the bases, the vector makes no sense. And the bases are not explicitly mentioned, then the implicit bases are the orthonormal set. Now, if I think of the vector eventually as a location in some space, I can represent that using different sets of bases, right? So this location, if I use my bases as x, y, z given by the red, blue, and green arrows, then a times x plus b times y plus c times z is going to get me to this location. But if I change my bases to something else, like these 3 guys, s, t, and u, then to get here, I might need a different combination of these 3 guys. I need to take some d steps along s, followed by, wait, no, that's right. So I have this backwards. So this is this mess over here, but yeah, this is like taking d steps along green, e steps along the blue, and f steps along u. If I change the bases, then the numbers in the vector are going to change while representing the same location. So in general, if you're not using the standard bases, you have to specify the bases to be understood. Vectors have lengths, and the length of a vector is simply the square root of the sum of the squares of the components. It's essentially the length of this displacement if you were using the standard bases, standard orthonormal bases. The Euclidean distance from the origin to the location of the vector when the vector is interpreted in terms of the orthonormal bases. That's the abstraction, right? But when we get to signals, where do signals turn up? No, if you change the bases, the length changes. So because if I change my bases over here, the length is defined in terms of, if I give you a vector of this kind, then the length is computed assuming orthonormal bases, regardless of what you actually intended it to mean, right? So the length of this guy is square root of a square plus b square plus c square. The length of this guy is square root of b square, d square plus e square plus f square, although the two of them represent the same location if you use x, y, and z as the bases here and s, t, and u as the bases here. The length assumes standard orthonormal bases. Yeah. But anyway, let's get to signals, right? We don't spend a lot of time with mathematical abstraction. Signals are frequently represented as vectors for manipulation. For example, if I have a segment of an audio signal, it's just a sequence of numbers, as we saw. But then I can just arrange them out in a vector, and now my little audio segment became a vector. Or here's another way of generating a vector out of an audio signal. I can take a little segment and compute a spectrum out of it. A spectrum represents the little segment of audio in terms of the frequencies present in it and how much energy there is in each frequency. So now this vector, this segment of audio, will have a spectrum of this kind where the x-axis represents frequencies and the y-axis represents the energy in the frequency. And this whole thing can just be represented as a horizontal arrangement of numbers where each number represents the energy in one frequency. So now here is a vector representation of the spectrum of this little segment of audio. For images, If I have an image of this kind, here's this image with 3 Pac-Man, those two can be represented as vectors. I just unravel all the pixels, arrange them out in a row, and now I have a vector generated from the image. I can always fold this set of numbers back, this vector back into the image, so long as I remember how I unravel the image. So that's just the basic of what a vector is. Now let's look at it in terms of, look at vector operations. There are 4 basic operations we can perform on vectors: addition, multiplication, inner product, and outer product. What's first? A vector, the first operation you can perform on a vector is multiplication by a scalar. So for example, if you have this vector, if I multiply that vector by the scalar 3, it means that every component of the vector is multiplied by the scalar 3. You're basically saying that the vector has been repeated 3 times. So 2.5 times the vector 3, 3, 4, 5 is going to give you 7.5, 10, and 12.5. Now, one of the outcomes of this, the fact that every single number in the vector is being multiplied by the scalar, is going to be, it should be 2.5. One of the outcomes of this is that the norm of the vector is also multiplied by the same scalar. Now, I'm not giving you anything new, right, so far. What's vector addition? If I add 2 vectors, literally what you're saying is that, firstly, the 2 vectors must be the same size and oriented the same way. If the number of components in the 2 vectors are different, you cannot add them. And you're literally performing component by component addition. The first component of the first vector adds the first component of the second vector, and so on. Now, this begins to make sense if you think of it in terms of how you're operating on the bases. 3, 4, 5 means that you're taking 3 steps along the first basis, 4 along the second basis, and 5 along the third basis. And this addition says that then you're going to continue the same operation according to the second vector. So you're going to take 3 more steps along the first basis, minus 2 steps along the second basis, and minus 3 steps along the third basis. So if you aggregate it all together, you've taken 6 steps along the first basis, 4 minus 2, which is 2 steps along the second, 5 minus 3, which is 2 steps along the third, right? Now, so addition's easy. One of the most important vector operations is the inner product. It is multiplication of a row vector by a column vector, and this results in a scalar. Note the order of operation. A row vector on the left will multiply a column vector. There's an order of operation to multiplication by amongst vectors. Again, this is all stuff that you're familiar with, so I'm not spending too much time on it. If I have 2 column vectors, A, B, C, if I want to compute the inner product between the 2, I have to convert the first one to a row vector before I multiply it by the second one. So that's if I have 2 column vectors, the first one is converted to a row vector by transposition. If I had 2 row vectors, then I would have to convert the second one to a column vector before I compute the inner product. In any case, the operation itself is going to look like this. The first component of the first vector multiplies this first component of the second vector. The second component of this first vector multiplies the second component of the second vector. The third component of the first vector multiplies the third component of the second vector. And then you sum them all up. So this is your vector inner product. So far, so good, right? Nothing new. What does this inner product operation actually mean? Again, the inner product between 2 vectors results in a scalar. What does it mean? We'll see. First, the inner product of a vector with itself is going to be the squared norm. You can see this immediately. It's going to be u dot u. An inner product is often represented with a dot, which is going to mean it's a multiplied by a plus b multiplied by b plus c multiplied by c. So it's going to be a squared plus b squared plus c squared, which is the squared norm of the vector. What about the inner product between two different vectors? That too has a meaning. So the inner product of two vectors tells you how much one vector explains the other vector. To give you a physical interpretation, let's say you're in New York, you're out here by Union Square, and you want to go up here to the Empire State Building. But then last night you had one too many, so you aren't too sure of your direction, and you ended up walking this way and then ended up at the Theodore Roosevelt birthplace. Is everything lost? Not really. The inner product between the two vectors says that, you still managed to get some way towards the Empire State Building. So in spite of being drunk, you managed to make some progress. And exactly how much progress did you make? That's what the inner product will tell you. It's the inner product between two vectors. Basically, it will tell you how much of this guy is explained by this vector or vice versa. But then let's look at it from a signals perspective. Here are three notes. This is me playing the note C very badly on my harmonica. That's the note E. That's the note C2. And these are their spectra, right? I can represent their spectra as vectors. Now just suppose I have a faulty harmonica. It cannot play the note E. It does have the first C. It also has the C in the second octave. Now I'm playing a little melody that needs the note E. So that needs the note. So wait, I'm playing a little melody which needs the note C. And my harmonica is faulty. It's missing the note C. Okay. So I decide to fake it. Instead of playing C, I play E. How good is it going to sound? Is it going to sound reasonable? What do you think? Anyone here done any music at all? You're very quiet. Okay. So how about if I play the same note C in the second octave? Is that going to sound... Here I have two choices, right? My C reed is missing in my harmonica. So I can fake it by trying to play the E, or I can try to fake it by playing the second C. Which of the two do you think is going to sound more reasonable? Anyone? C2, right? Can you give me a mathematical description, explanation of why? Voila, the inner product. So exactly, Manohar, right? If I look at the spectrum of C and the spectrum of E as vectors, and the spectrum of C2 is also as a vector, these are actual values from this example. The inner product between C and E is 0.1. E doesn't explain C very much at all, which is why when you try to play E instead of C, it's going to sound crappy. On the other hand, if I look at C2, the inner product here happens to be 0.5. C2 does a pretty darn good job of explaining C, which is why I can maybe get away with a bit with playing the same note in the next octave. To get a physical intuition for why this works, in the second octave, all of these frequencies are scaled up by a factor of 2. So when I take an inner product, I'm lining up the frequencies for both notes and taking a frequency-wise multiplication and summing them up. Here, between C and E, the frequencies don't match at all. So when I take a frequency-wise product, every time this guy has a valid frequency, this guy has zero energy in that frequency. For every note of this one, every frequency with non-zero energy here, that frequency tends to have zero energy out here. And so the inner product is really poor. Whereas if I take C and C2, for every second frequency of C, C2 has a corresponding component. And so when I take an inner product of the two, I'm going to be multiplying significant numbers, and the inner product will be quite high, which is why C2 does a better job of explaining C than E does. So you get an idea of what an inner product is. An inner product gives you a mechanism for one vector to explain another. And correlation is an inner product, right? Perfect. So moving on to our next concept, vector spaces. How do you define a space, anyone? How do you define a space? Okay, that's a region, right? Conventional notion of a space is a geometric construct of a certain number of dimensions, like each of you is sitting in a three-dimensional space. And every object, you and every other object, live in that three-dimensional space. In math, you speak of vector spaces. A vector space is an infinitely large set of vectors, must be infinitely large, which has the following properties. It includes the zero vector, which is a vector of all zeros. If a vector x is in the set, then a times x must also be in the set for any scalar a. It must be closed under addition. If x and y are in the set, then a times x plus b times y must also be in the set for any a and b. And because it includes, because of the first property, right? Because it includes the zero vector, then for any vector x, it must also include the additive inverse, some y which equals minus x, such that x times y is 0. If these properties are satisfied, then this set is called a vector space. For every x, ax must be in the set. If I add any two entries in it, the result must also be in the set. There must be a zero vector, and every vector must have an additive inverse. These are the requirements. There are some additional requirements. Scalar multiplicative identity element must exist. So there's a scale. If I multiply x by 1, the result must be x. Addition must be associative. X plus y is y plus x, commutative. And the scalar multiplication is commutative. But the first four properties capture most of it. So let's take a look at some examples. Here is a vector space. It's the space of all three component vectors where the components are real. Now, can you verify that this is actually a space, vector space? Does this include the zero vector? Anyone? Is it, if I multiply by a scalar, is the result in the set? If I add two entries, is the result still in the set? And is the negative of every vector also in the set? So this is a vector space, right? Here's another one. This is the set of all functions of the kind a cos x plus b sine 2x for x lying between minus pi and pi. You're speaking of functions. You're drawing a plot across x between minus pi and pi, but the functions have this form a cos x plus b sine 2x, where a and b are real. Is this a vector space? Does this include the zero vector? It includes the zero vector, right? If a and b are 0, you have a zero vector. And it cannot be a vector space without me actually defining the addition operation. So I'm going to define addition of two entries, f plus g of x, as f of x plus g of x. Once I define addition this way, you can verify this is a vector space. It includes the zero vector. The sum of any two entries is also going to be in the set. And every entry has its negation. For a cos x plus b sine 2x minus a cos x minus b sine 2x is also in the set, right? So this is a function space. It's a space of functions, but it's still a vector space. So now we get to the notion of the dimension of a space. If I have a vector space, every element in the space can be composed as a linear combination of some other elements in the space. For any x in the set S, I can write x as ay1 plus by2 plus cy3 and so on, where y1, y2, and y3 are in the set. What's a trivial way of proving this? Can anybody prove this? Anyone? So here's what I can do. For any x, I pick some other y, and then I create two, or I pick up a z, and then I create two vectors. Y1 is x plus z, y2 is x minus z. And by the properties of the vector space, both y1 and y2 must be in the set. But then y1 plus y2 is going to cancel out the z, and it results in x. So it's trivial to show that for any x and s, I can always write it as a combination, as a sum of some other entries in the set. Now, pardon my coughing. So pretty much every entry in the set can be expressed as a sum of other entries, but there are some subsets of elements that have the special property that using just those guys, you can compose every other element in the set, basically the entire set. So there's a smallest subset of elements that can compose the entire set. The smallest subset of elements that can compose the entire set are called the bases. And the subset is the basis set. And the number of elements in the subset is called the dimensionality of the space. So here, for example, if every element in the set can be written as some a1x plus b1y plus c1z for this guy, some e2x plus b2y plus c2z for this one. So every one of them can be written as some linear combination of x, y, and z. And there's no set with fewer than 2 or 3 elements that satisfy this property, then the dimensionality of the space is 3. Let's look at some examples. What is the dimensionality of this vector space? Anyone? 3? Correct, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the dimensionality of this space is 3. Here's another space. Is this a vector space? Does this include the 0 vector? Does it include the inverse of every vector, additive inverse? Obviously, for every a, I take a minus a. For every b, I take the minus b. What is the dimensionality of the space? It's 2, right? I just need the vectors 1, 2, 3, and 4, 5, 6 can be used to compose every element in the set. So although there are 3 components to the vectors, the dimensionality of the space is just 2. Right? That makes sense to you guys? Yes or no? Right. So, okay, here is a poll for you folks. And can you see the poll? Okay, 10 seconds, guys. All right, let me end the poll. And I'll share the results. There are a variety of results. I'm going to ask the guys who answered 2. Why do you think the dimensionality of this space is 2? Anyone? Why is the dimensionality of the space 2? Exactly. Is cos x part of the space? What about sine 3x? And so just cos x and sine 3x between them can compose every element in the set, right? So there are just two entries in the set, which can compose every element in the set. So what is the dimensionality of the set? 2. That makes sense to everybody? So I'm assuming, yeah. So, yeah. Then, yeah, if cos x cannot extend sine 2x, sine 3x. So this is 2, right? So that's abstraction. Then, so if I had cos x and cos x, then the dimensionality would be 1. But you cannot explain sine 3x with cos x. So returning to dimensions, we see that there are two interpretations of the term dimension. There's the spatial dimension of a vector. So for example, over here, the spatial dimension of the vector was 3. This is the standalone definition of a vector against standard basis. If I just give you a vector, it has a certain number of components. Ask you what is the dimension, you're going to give you, say, the dimension is the same as the number of components. But then there's the embedding dimension of the vector, which is the dimensionality of the subspace that it lives in. And that only makes sense in the context where the vector is an element of a set. If I say here is a set like this one, then you find that all elements in the set can be explained using just 2 vectors. And in this case, the dimensionality is just 2. So the embedding dimension of the set, of the vectors of the set, is 2. But the spatial dimension of the individual vectors is 3. Does that make sense? The difference between the two? So look at this set. If I give you just the vector 1, 2, 3, then what is the dimensionality of that vector? It's 3, right? In the absence, when you look at that vector standalone, the dimensionality of the vector is the number of components in the. But if I give you can you mute yourself, guys? Folks, can you mute yourselves, please? Right. I'm not sure how to mute people. Okay. We'll try. Whoever is unmuted is very noisy. Okay. So, where was I? I lost my chat. Okay. So to answer your question, Aryan, if I give you just a standalone vector, the dimensionality of the vector is the number of components in it, right? But if I tell you the vector is a member of this set can be composed using only 2 vectors, correct? So the dimensionality of the set is 2. Did that answer your question? Which x is a variable? I'm not sure. There is no x over here, right? Yes, Aryan. We need the added context to determine the dimensionality. The poll question, it doesn't matter. This is a function over here, right? That's what we meant by a function space. Think of the picture. Here I am drawing a plot between minus pi and pi. This is the set of all plots, which can be written as a cos x plus b sine 3x. Did that answer? Right, Shashi? Did that make sense? This is the set of all function plots between minus pi and pi that have the form a cos x plus b sine 3x. So x is just an indicator, but it's just as, this guy has 3 components. Here, every entry has an uncountable infinity of components going from minus pi to pi, and they form a shape. And that's your vector. Does that make sense? Right, okay. So it took us 40 minutes to get to matrices, darn it. I am behind. what's a matrix? It's a rectangular or square arrangement of numbers. This is a 2 cross 3 matrix. It's got 2 rows and 3 columns. This is a 3 cross 3 matrix. How do I have so many mistakes? Right? So a matrix is specified which one? So which constraint? There was no constraint over here. I'm defining the set in this manner. Yeah. Right. And if I define the set in this manner, then the dimensionality is 2. Now, so the size of a matrix is specified by the number of rows and columns. This is a 3 cross 1 matrix, 3 rows, 1 column. This is a 1 cross 3 matrix. Matrices with just 1 row or 1 column are also vectors. This is a 2 cross 2 matrix. This is a 2 cross 3 matrix. This Pac-Man is a 321 cross 399 matrix. It's a rectangular arrangement of numbers. Now, a matrix can be transposed, and when you transpose it, it gets all its rows and columns transposed. So you're basically flipping it along its diagonal. You're familiar with this operation. This column matrix, when transposed, becomes this row matrix. This row matrix, when transposed, becomes this column matrix. Easy operation. I can do it for images. This is a picture of my good friend Chris Ran. And when I transpose him, this is what he looks like. It's a matrix transposition. So we know what it means, right? Yeah, so matrices are rectangular arrangements of numbers. But what is a matrix? A matrix by itself is completely uninformative, except through its relationship to vectors. So vectors are key to defining matrices. Again, we can get more abstract, and in a more abstract sense, matrices can themselves be vectors, but I won't go there, right? So we're going to look at 3 ways of interpreting matrices. Matrices can be interpreted as transforms, as data containers, and they can be interpreted as compositional building blocks for vector spaces. So let's look at matrices as transforms. Here's a matrix. When a matrix can multiply a vector, we are all familiar with it, right? So this matrix A could be multiplying this column vector B. And so when you have a column vector, it must be left multiplied by a matrix. And the result is going to be this vector, where the first entry is going to be A11 times B1 plus A12 times B2 plus A13 times B3 plus A14 times B4. The second one similarly multiplies the numbers in the second row by the vector, entries in the vector to compose the second term. And the third row over here is obtained by multiplying the numbers in the third row of the matrix by the entries in the vector. So clearly, the number of columns in the matrix must be equal to the number of rows in the vector for this operation to be possible. And so the result is going to have as many rows as the number of rows in the matrix. Again, we're familiar with this, right? Similarly, if I were multiplying a matrix by a vector and it's a row vector, then the matrix must be to the right of the vector. And in this case, the result is going to be a row vector also. And we know exactly how it's done. I've written it in transposed form over here because it wouldn't fit on the screen. But the first entry is going to be B1 times A11 plus B2 times A21 plus B3 times A31. The second entry is going to be B1 times A12 plus B2 times A22 plus B3 times A32 and so on. So the matrix must have as many rows as the number of columns in the vector. The dimensionalities must match. And the result will have as many rows as the number of rows in the matrix. Right? Easy. But then what happened here? In both cases, the matrix operated on a vector and produced another vector. Here it operated on this vector B1, B2, B3, B4 and ended up with this vector. Here it operated from the right on this row vector and ended up with this row vector, right? So a matrix transforms a vector. It starts off, it takes some vector, it operates on it, and the result is going to be an entirely different vector. What is the relationship between these two guys? Or if I were to transform every vector in the space, how will it modify the space? So let's start off with this very simple example. Let's consider all the vectors on this circle, right? If I were to multiply all the vectors on this circle by a matrix, transform them with a matrix, what will the resulting picture look like? What will the shape be? Anybody? It's going to be an ellipse, right? So here I have very conveniently color-coded all of the points in the circle. I multiplied it by the matrix, and these two vectors here actually show the row vectors of the matrix itself. And when I do it, this thing becomes this ellipse. And the exact position, you can find out where each vector went by comparing the colors. So even the row vectors of the matrix itself are going to be displaced. So it's, as you can see, it's scaled and rotated the space. When you convert a circle to an ellipse, you sort of stretch it and rotate it. So it's scaled and rotated the space, including its own vectors. Now, how do the coordinate axes in the new space relate to the matrix? Anybody know? How do they relate? It's actually fairly simple. You take the row matrix, row vectors here. The vector, the x-axis over here is going to be the vector that's orthogonal to the first row vector here. The y-axis over here is going to be the vector that's orthogonal to the second row vector here. So you can just, the new axes are going to be the vectors that are orthogonal to the rows of the matrix. So cool, huh? What if I go up into higher dimensions? So here's something where I've multiplied three-dimensional vectors by a 3x3 matrix. What are the new axes? The new x-axis over here is going to be the vector that's orthogonal to the second and third rows of the matrix. The new y-axis over here is going to be the vector that's orthogonal to the first and third rows. And the new z-axis is going to be orthogonal to the first and second rows. So you can just inspect the matrix and you can determine the directions of the bases in the new space. That makes sense to you guys? It's easy to prove, but you can take these on faith. Questions? Okay. So the new x-axis over here is going to be the vector that's orthogonal to, depending on how you order x and y, the new x-axis here is going to be the vector that's orthogonal to, in this case, the second row vector, actually, of y. And the new y-axis in the transform space is going to be the vector that's orthogonal to the first row vector. So the vectors that are orthogonal to the row vectors of this matrix are going to be the bases in the new space. That answer your lesson? Same thing. Right? So over here, the new x-axis is going to be the vector that's orthogonal to everything except the first row. The new y-axis is going to be orthogonal to everything except the second row, and so on, right? So it's orthogonal to the, so the new x-axis is going to be orthogonal to this hyperplane composed of these two guys. So that's matrices as transforms. But what is the second use of matrices? They are data containers. They can be thought of as a vertical stacking of row vectors or a horizontal arrangement of column vectors. So the space of all vectors that can be composed of from the rows of the matrix is called the row space, and the space of all vectors that can be composed from the columns is called the column space of the matrix. And we will often use matrices as data containers, not just as transformers. For example, if I have an audio signal, I can convert it to a spectrogram like so. A spectrogram is actually composed of many spectral vectors. And now this entire spectral vector, the spectrogram is going to be a matrix where every column over here of the matrix represents a spectrum of one little segment of the audio signal. And so now I have a matrix, but the columns of the matrix represent spectra, and the matrix is just a stacking of column vectors. This is a data container, right? Or if I have an image of this kind, this image is a matrix where every column represents one column of pixels, right? So, but then if I unravel the matrix, the images, here is a collection of spectra. This is again the 3 notes. I can pack these 3 spectra into a matrix. And so now this matrix is a data container containing these 3 spectra. I can unravel each of these faces and make them columns of my matrix. And now this matrix is a data container containing all of these images. So matrices can be data containers. Matrices can also be compositional building blocks for vector spaces. How so? Now look at what happens when I right multiply a matrix by a column vector. Here's a matrix. I've right multiplied this by the column vector. We saw one way of viewing how the result is computed. But then if you look at what's happening, this is simply mixing the 4 columns of the matrix. The first column is multiplied by B1. The second column is multiplied by B2. The third column is multiplied by B3. And the fourth column is multiplied by B4, and then you add them all up. So right multiplying a matrix by a column vector is basically mixing the 4 columns of the matrix to compose a new vector. So the matrix, you're basically as you keep changing this column vector, you're mixing these 4 guys in different ways. And so what do you get when you mix vectors? You get a vector space, right? And so the matrices can basically be viewed as space constructors, where you can compose entire vector spaces by mixing their column vectors. Or if you so choose, if you want to left multiply the matrix by row vectors, then in this case, the result is going to be the first entry multiplying the first row, plus the second entry in the row vector multiplying the second row, plus the third entry in the row vector multiplying the third row. And so that's going to be give you a, when you left multiply a matrix by a row vector, you're mixing the rows of the matrix to get a new vector. Again, now the rows in the matrix are being used to compose a space. So matrices can be space constructors, right? Let's look at a physical example. Here again are my 3 favorite nodes, right? I've stacked them into a matrix. How can I come up with all the ways of mixing these 3 nodes? All I have to do is to right multiply this matrix by the appropriate vector to come up with any particular combination of these 3 nodes. So if I multiply this matrix, which is simply obtained by the stacking of these 3 vectors, by the vector 1, 1, 2, 1. I'm going to get 1 times the node C plus 2 times the node E plus 1 time the node C2, which you can hear, right? And so this is my way of mixing bases or mixing units, nodes, or images. Let's say I have this image of the Arecibo telescope. I think in Puerto Rico, and then there's this image of Pac-Man. I can unravel both and they both become column vectors. And now I can form a matrix by just packing those 2 side by side. What is an image that's 0.25 of this vector of the telescope and 0.75 of the Pac-Man look like? I just multiply this matrix by the 0.25, 0.75 vector, and that mixes these 2 columns. 0.25 of this guy and 0.75 of this guy. And when I display it as an image, here's what you get, right? So here are the interpretations of a matrix. They are transforms that modify vectors and vector spaces. They are data containers of data, and they are generators of vector spaces. Questions? Any questions? No. So now let's look at matrix operations. What is the outer product? The outer product of two vectors is the product of a column vector by a row vector. It's also called the vector direct product, and this results in a matrix. This is going to be, if I multiply this column vector ABC by the row vector DEF, the result is going to be the first column AB is obtained by multiplying ABC by D. The second one is obtained by multiplying ABC by E. And the third one is obtained by multiplying ABC by F, right? So inner product, we are not even speaking of the inner product between matrices. The inner product is between vectors, right? So that's something that we should probably take off. That's a little more sophisticated. We should take it off to the answer. But then, so what does this matrix outer product really mean, right? This is very easy for me to just state, but can I give you a physical meaning for this? I can think of this as a basis, and I can think of this as a modulation. So here, for example, I have a spectrogram for a node. This is my column vector, and I want to modulate it according to the sinusoid. So what do? I compute the outer product of this node and the modulation. And it gives me the spectrogram, which is a matrix, which gives me this node modulated by this pattern. So an outer product can be thought of as modulating a vector across the second dimension. So that's just a single vector, right? Now we know how matrix multiplication works. When I multiply two matrices, then if I multiply this matrix A by this matrix B, we know exactly what the result is going to be. This top left corner is going to be obtained by multiplying all the elements in the first row here, element-wise, with all the elements of the first column, element-wise, and summing this up. The second entry is going to be obtained by multiplying all the elements of the first row by all the elements of the second column. In general, the ijth entry is going to be obtained by multiplying all of the elements of the ith row by all of the elements of the jth column, and then summing them up. This is the standard formula for matrix multiplication. All of us are familiar with this, right? Everybody remember this? Yes or no? Yeah. Just one person remembers. Okay. Fine. Thank you. But then, you know what? There's a different way of thinking about it. And there are a couple of different ways of thinking about it. And you can think of everything in terms of two operations. One is the inner product between mate vectors, and the other is the outer product between vectors. This is the outer product. We already know what the inner product looks like. So I can think of the left matrix as a column vector where each entry is a row vector. I can think of the right matrix as a row vector where each entry of the row vector is a column vector. And then when I think of it this way, this product is essentially the same as this guy. Do you see that? If I replaced A over here by a row vector and D over here by a column vector, then you end up with this. Then this is exactly, right? Do you see how this and this are the same? Just by thinking of the individual entries as, so this is a vector outer product. If I think of a matrix as a vector of row vectors and this guy as a row vector of column vectors, then this is just your standard outer product, vector outer product, right? Similarly, I can flip that. I don't need to think of this as a row vector of column, as a column vector of row vectors. I can think of the left matrix as a row vector of column vectors and the right matrix as a column vector of row vectors, right? And this looks like an inner product, does it not? It's going to be this guy times this guy, plus the second entry here times the second entry here, plus the third entry here times the third entry here, and so on. So does anybody see the similarity between this and the inner product? Anyone? Anyone else? Right. And so this is beautiful, right? When I multiply two matrices, the result is the first column times the first row, plus the second column times the second row, plus the third column times the third row, and so on. It's beautiful. And how does that help me? Right? Why is it useful to think about things this way? It's one of the basic ways of building things. So, for example, suppose I have these three nodes, our favorite three nodes. Since that's all I managed to play on that day. And I want to create a little bit of music where I modulate this first note in this way, the second note according to this red curve, and the third note according to this curve. What do? First, I pack these three notes into one matrix. I pack these three modulations into a second matrix, and then just multiply the two, right? And when I multiply the two, I'm going to have these three notes and their corresponding three modulations. And the product, of course, is going to be the first column times the first row, which is going to give me this, plus the second column times the second row, plus the third column times the third row, which is going to give me this. And so I have my result. So the matrix multiply can actually be viewed as a sum of modulations. I don't know if you have thought about it, but I think that's a very beautiful way of looking at things. That's a beautiful interpretation. Questions? Or here's another one, right? How many of you have seen any of those cheesy black and white movies from the 1940s? I'm sure somebody must have caught something on Netflix or something, right? And if you've seen those, you often see these crazy little animations where one image fades in and another image fades out. So let's say I want to fade from this image to this. I want this image to fade out and this image to fade in. What do? I pack both images as column vectors. This one's modulation is my first row vector. This one's modulation is my second row vector, and I just multiply the two. And so the product is going to be the first column times the first row, which is this fading out, plus the second column times the second row, which is this fading in. And so the result is going to give you this image at the bottom, right? Cheesy 1950s movie. But again, a matrix multiply can be thought of as a sum of modulations. Matrix operations have their own properties. They are, A plus B equals B plus A. So the actual interpretation is that if I transform any vector by the sum of A and B, it's the same as transforming it by the sum of B and A. And of course, they're associative. It doesn't matter how you group the operations. So addition is associative, so is multiplication. It's distributive. A times B plus C is AB plus AC, but it's not commutative. A times B is not equal to B times A. Why is this so? Rotating, you can think of a rotation is a matrix operation. So rotating right by 30 degrees and rotating down by 30 degrees is not going to give you the same as rotating down by 30 degrees and then rotating right by 30 degrees. You'll end up in different places. And then there's the transposition rule. The transpose of A times B is B transpose times A transpose. I happen not to be in the classroom, but then you can actually, if I were, I'd be showing you how this makes sense with the ruler. But I assume you just know this. When you transpose the product, it's going to be the product of the transposes in reverse order. So here is my second poll for the day. Great. Gotta stop sharing this. Can you see the poll? Okay. Ten seconds, guys. Okay, let me stop this. Let's answer the questions, right? Actually, I have the answers here. Transposition property is true for matrices, right? So is the distributive property, and so is the associative property, but it's not commutative. You can't, when you multiply two matrices, you can't change the order. Also, A plus B times X is the same as B plus A times X because addition is commutative. So now here's the crazy bit. Matrices are actually vectors themselves when you look at them differently. The set of all matrices of a given size is a space. And for specific kinds of matrices, it will be a vector space. So if I take the set of all 3 cross 4 matrices, I can add them component-wise. And the result is going to be a 3 cross 4 matrix. So it's closed. If I multiply a matrix by a scalar, it's going to give me another matrix of the same size. So scalar multiplication is closed. The zero matrix exists, and matrices have additive inverses, and associativity and commutativity rules apply. So amazingly enough, matrices are themselves vectors in a vector space. This making sense to you guys? Right? Amazing, yeah? So now let's look at various matrix types. The identity matrix is a square matrix where all the diagonal elements are 1 and the off-diagonal elements are 0. I call this the lazy or the do-nothing matrix. When you transform a vector by an identity matrix, nothing happens to it. So it's a do-nothing matrix. A diagonal matrix is one where the off-diagonal elements are 0 and the diagonal elements can be anything. So all it does is it scales the axes. Each element scales the corresponding axis by the value of that element. So this 2, 1 diagonal matrix is going to scale the x-axis by a factor of 2, and the y-axis is going to be scaled by 1. And the effect on the circle is shown in the figure, right? It gets stretched out. There's something called a permutation matrix. A permutation matrix simply rearranges the axes. So here, for example, this is a permutation matrix. What happens? If I multiply an vector x, y, z by this matrix, the permutation matrix always has this property. All of the rows are going to be all 0 except for one entry, which is 1. And the position of the 1 is going to be different in all of the rows. So if you look at this guy, if I multiply x, y, z by this matrix, the first entry is going to just be y. The second entry is going to be z. And the third entry is going to be x. And so it just rearranged the order of the components. So this is a permutation matrix. It permutes the arrangement of elements in the vector. Now rotation. If I take a vector and rotate it by some angle theta, it's going to result in another vector x prime y prime, where the relationship between x prime y prime and xy is given by this. X cos theta, x prime is x cos theta minus y sine theta. Y prime is x sine theta plus y cos theta. And this is something you know from trigonometric class, but I can write this as a matrix operation. I can have a rotation matrix, which is cos theta minus sine theta, cos theta. And so you will see that the vector, new vector x prime y prime is simply r theta times x. So a rotation matrix rotates the vector by some angle theta. Alternately, you can think of it as saying it keeps the vector constant and rotates the axis by some angle theta. So typically, any matrix operation is going to be a combination of rotation, permutation, and stretching. It doesn't matter what your matrix is. I can show you that eventually it's just a combination of a rotation, a permutation, and stretching. So every matrix operation is going to be some combination of rotations, permutations, and stretching, which is kind of cool, right? Questions? Okay. The last set of topics, please stay with me till I just get through these three. Matrices have something called rank. Some matrix transformations will eliminate one or more dimensions during transformation. So for example, if I were transforming all the elements in this cone by some matrix P and the result flatten the cone into this two-dimensional object, then the result has one dimension less, even though it's in 3D space. It's been squashed into a 2D object, right? So it has eliminated a dimension. A matrix which will do this is a rank deficient matrix. And the rank of the matrix is the number of dimensions that you have when you end up with when you transform a full dimensional object. Here, for example, a three-dimensional object has been squashed into a two-dimensional surface. So the rank of this matrix is 2. So here's an example. This cone, when transformed by this matrix, ends up becoming this little two-dimensional patch. The rank of this matrix is 2. If I multiply all of the elements on this by this guy to the right, it just becomes this line. So it has reduced the cone to a one-dimensional line. So the rank of this matrix is 1. So in general, the rank of the matrix is the dimensionality of the transformed version of a full dimensional object. Non-square matrices are going to add or subtract axes. So if I take a sphere of this kind in 3 dimensions, and then all the elements on the sphere are vectors which I can put into a data matrix, right? If I transform all of these vectors by a 2 cross 3 matrix, the result is going to be a whole set of 2-dimensional vectors. And that's going to be living in a 2-dimensional space. So when the matrix is wider than it's tall, then you transform a full-bodied object, it's going to end up with as many dimensions as the number of rows in the matrix. So this is going to become a 2-dimensional ellipse in a 2-dimensional space. Now, I can also go from multiply this object by a matrix which is taller than it's wide. So if I multiply an object by a matrix that's taller than it's wide, it's going to increase the spatial dimensionality of the object. But the embedding dimensionality is going to stay the same. So here, for example, if I squish this sphere down to this 2-dimensional ellipse using this 2 cross 3 matrix, now if I multiply this 2-dimensional object by a 3 cross 2 matrix, the resulting vectors are all going to have three components. So they're going to be living in three-dimensional space. But the dimensionality of the object itself is not going to change. It's now just going to become a two-dimensional disk in three-dimensional space. So a matrix can never increase the number of dimensions of an object. It cannot convert a circle to a sphere or a line to a circle. What this means is that since the rank of a matrix is the dimensionality of the transformed version of a full dimensional object, when I transform a three-dimensional object using a 2x3 matrix, it's going to become a two-dimensional object. So the rank of this matrix is 2. And even if I go back to three-dimensional space, now the object is going to stay in 2 dimensions, which means that the rank of a matrix can never be greater than the lower of its 2 dimensions. Whatever the output of the transformation by the matrix, the number of dimensions in it is going to be equal to the lower of the number of rows or the number of columns. That makes sense? Yes or no? Okay, easy, right? So we can also think of a rank in terms of the number of bases. We'll get back to this shortly. So that's the rank of the matrix. If the columns of the matrix are linearly dependent, then the rank is going to be smaller, right? There's one third poll for today, and then I'll look into one final subject. Can you see the third poll, guys? I'm only giving you 20 seconds for this. So please be quick. That's going to be R3 in 3D. Yeah, my copy paste went bad. All right. I'm going to stop in 5 seconds, guys, because I'm running out of time. Okay, what's the answer to the first question? Anyone? Okay, since you're quiet, let me just give it, right? Given a circle in R3, there will always be a matrix such that the image of a circle under transformation will be a sphere. No, it's a circle. You cannot increase the dimensionality, right? And a square matrix with n rows and n columns will always have rank n. No. A square matrix, as we saw in some of our examples, can have rank lower than the number of rows and columns. So moving on, the final topic. This is going to take, I'm going to go over by a couple of minutes. How many of you are familiar with the concept of a determinant of a matrix? So what do you understand by determinant? What is a determinant? What is the physical volume, Alex? How? Volume of the parallelepiped of the row vectors, okay? Of the unit cube, sign volume. Right. So what do you mean by volume? How does that relate to it as a transform? How does the determinant of a matrix relate to it as a transform? So let's get to it, right? Here's how a determinant is typically defined. If I have a matrix of this kind, A, B, C, D, then there are 2 row vectors, A, B, and C, D. Here are the 2 vectors, and then there's a vector A plus C, which is the sum of the 2. I get a parallelogram, and the area of this parallelogram is the determinant of this matrix. Here's another matrix. I have 3 row vectors. I can have R1, R2, and R3. Then the sums of pairs and the sum of all 3, it's going to give me a 3-dimensional parallelepiped. and the volume of this guy is the determinant of this matrix. Did that tell you anything about the matrix? Nothing, right? It doesn't tell you how it's going to change an object, but Manohar is right. So here's what a determinant means. If I've got a full volume object, let's say a unit sphere, and I transform it by a matrix, it's going to end up as a new object in the new space. If it's a square matrix, then if I'm starting from 3 dimensions, it's going to end up in a 3-dimensional space. And this object will have some volume too, right? When I transform the transformed object is going to have a different volume than the original object. Now, can you tell me, now that I've given you the hint, how does the determinant relate to the volumes of the two objects? Anyone? The ratio of these two volumes is the determinant of the matrix. The volume of this matrix is scaled by the determinant of this matrix. The volume of this object is scaled by the determinant of this matrix to give you the volume of this object. And so the determinant of a matrix is the scaling factor by which the volume of a full-bodied object in the original space is modified or scaled in the output space. So clearly, and it's very useful to think of it this way. This is in fact the only real interpretation of determinant. So clearly, we're always speaking of volumes, so that there are some additional interpretations to be made over here. First, matrix determinants are only defined for square matrices. They characterize volumes in linearly transformed spaces of the same dimensionality as the vectors. Rank deficient matrices have determinant 0. Why? Because if I multiply this object by a rank deficient matrix, the resulting object is squished. It's lost a dimension, which means its volume is 0. And so, if the matrix is rank deficient, it's going to be eliminating some dimensions. It's going to result in a 0 volume object, which naturally means that it's going to have a determinant of 0. And conversely, all matrices of determinant 0 are rank deficient because they compress full volumed n-dimensional objects into 0 volume objects. And also, this is my last slide, gives you some properties for determinants. What is the determinant of the product of 3 matrices? You're literally saying if I scale an object by the product of 3 matrices, then how much does the object get scaled by? This is the same as saying I'm going to first scale it by C, then I'm going to scale the result by B, then I'm going to scale the result by A, right? And so the determinant of a product is going to be the product of the determinants because it's the product of the scaling factors. Note that matrix multiplication itself is not commutative, but from the determinant perspective, it is. On the other hand, the determinant of B plus C is not the determinant of B plus the determinant of C. And once again, it's trivial to figure this out if you think of it in terms of scaling factors for volumes, and it's commutative. The order doesn't matter. The determinant of AB is the same as the determinant of BA, which is the determinant of A times the determinant of B, because it's all about scaling factors. I'll stop right here. And I think I've gone just a bit over. I apologize.